Hello, welcome to Know the Score for Multifactor Strategy of Experimentation. This is Mark Anderson from Studies Incorporated. Today we'll talk about screening, characterization, optimization, and ruggedness testing. SCOR, Know the Score. I'll be presenting today. I'm engineering consultant. My background is professional chemical engineering and certified quality engineering, and I have my master in business administration. I've been working with design of experiments for approximately 50 years, beginning in 1974, when I first started doing research and development, not knowing a thing about statistics or design of experiments, and particularly the idea of using multi-factor approach. Had no knowledge of that. It wasn't taught in high school chemistry or chemical engineering at University of Minnesota or anywhere along the way. You were just expected to know pretty much what was going to happen, make a couple of tries at it, and you should succeed from sheer brain power. Obviously, that cannot work. And so I'm happy to talk to you today about some very effective approaches for industrial R&D to organize your experiments in a whole program that covers the screening first, then the characterization, possibly optimization, and then some sort of verification at the end, which I suggest would be ruggedness testing. So I'll go ahead and start the show now. And the first thing then is to make sure that everything's working okay. So if you would press that raise hand button on the GoToWebinar control panel, then I'll know that you can see the slide and hear me speaking. All right, I'm getting some feedback immediately from Peter, Alan, etc. Thanks, everybody. I'll put the hands back down again. So I'm going to keep you on mute just because with the numbers of people that are involved, it's easier that way and not to run into problems where they forget to turn off their microphone. I will not be looking at chat along the way. I may look at it afterwards, but I'm not going to give a guarantee on that either. So what I really suggest is that you address any questions you have, make a note of it with the slide number if you're at a certain slide, and then send it to me directly, mark@staties.com. The presentation will be posted to our webinar site, and the recording will go to the YouTube. You can link to it through the webinars or go to the Staties YouTube channel directly, and you'll eventually see the presentation posted. All right, so again, welcome, and let's talk about knowing the score, the strategy of experimentation. So the WIFM, what's in it for me is that by example, this presentation will lay out a strategy that can be very effective for accomplishing your goals for industrial R&D, or possibly you could be working at an academic level, doing graduate research or funded research, and these type of tools would be very good for that as well. So applying a strategy, of course, is always good, and trying to make the most out of your time and quickly come to a point where you either succeed in achieving your goal or you come to realize that you're just not on the right track at all, and you can fail fast and move on to the next project. If it works, then in the end, by doing confirmation runs, especially using ruggedness, then you'll end up with a robust process that should be reliable. So that's the first thing. And the second thing is that in the end, you can look at multiple responses and you can find a sweet spot that meets all the requirements or product attributes. All the way up and down the line, you can meet everything and hopefully do it in a way that is quality by design, in that if you drift a little bit from your set point that you establish, it won't cause the process to go out of specification. This is a presentation that can work if you're new to design of experiments or experienced because of the strategy that's being presented. And maybe you know about this, but you can listen to my presentation and you can help convince other people to do the same thing, to use this multi-factor approach and then apply a good strategy. Okay, so as a preamble, before you can begin this whole series of experimentation, you've got to be in the right neighborhood, and that requires a great invention. So somebody's got to come up with some kind of a brainstorm. Here's a literal brainstorm by Art Fry, sticking this Post-it that he invented on his head with a light bulb on it. And so hopefully that light is flickering on and you're coming up with some kind of a great idea, even if it supposedly is by accident, which is the story with Art Fry, in that he was trying to make a stronger adhesive and realized that that weaker adhesive could be used for these temporary sticky notes. Another Minnesotan that I want to call out here is Rain Geyer, who is the Nerf genius. And so somehow came up with this initial idea, and from there, they developed it and came up with a product that really works and has come out in a variety of formats. And then last but not least, I want to pay homage to Hormel, or Hormel, depending on how you want to pronounce that. I was born in Austin, Minnesota. My father is a master civil engineer, and he is working on Hormel wastewater treatment operations. And so this strikes right back to home. Of course, their famous product is Spam, and it really hits the spot if you have no other way of transporting meat. So during World War II, I think it was pretty popular, and you can still pick up some pretty nice meals on Spam in Hawaii, for example. It's kind of a comfort food there. So they put a lot of work in at Hormel to develop this product, and I actually have done consulting with them over the years on other types of products, and they are very strong on using design of experiments. So we need to start with a great invention. Once you have that and you're getting close to where you need to be, then we can start applying the strategy of experimentation. And I do want to say at the outset that we're going to be focusing on multi-factor rather than one factor at a time, of course, and that's the core of DOE. And also we're going to focus on process. All right, although the same sort of strategies can apply to developing a new product with mixture design for optimal formulation, it's slightly different. So I'm going to focus on process, but you can apply the same basic ideas of screening, many unknown components, but in this case, I'm going to talk about factors, again, with the focus on process. Now, the nice thing about this screening approach is that oftentimes you're working with people that are very strong in subject matter knowledge, and they have some experience, and they kind of jump to certain conclusions, which are probably pretty good, that they know some of the key factors. And so we might know, if we're doing some kind of cooking operation, that obviously temperature is going to be an impactor, time, things like that. Okay, but if you're going to do a really comprehensive job, it pays to start with a broad and shallow screening first and do what we call a medium resolution 2-level fractional design is what I would recommend. And the design that I would suggest, if I go over to our tools, which I'm showing Statis 360, which is a superset of Design Expert, the 360 adds in, the biggest thing is this Python script editor in case you're able to do programming and go to the world of Python and bring in some connections there, then this 360 would be for you. If you're not into the programming, then go with the Design Expert that'll have all the tools I'm going to demo here. And the first suggestion I'm going to have would be, if I was going back in time working as an R&D engineer and I had this tool back in the 70s and didn't have to use a mainframe timeshare and do things by hand with pencil and paper and a slide rule, I would have pulled up this design option here, which is got 8 factors, but not all 256 combinations, 2 to the 8th power, not a half fraction, quarter fraction, 8th fraction, but going to this 1/16th fraction, which is a natural minimum run option that has as many factors as you can get in a minimum number of runs and still be able to resolve the main effects, because our goal here is to resolve the main effects. So I'm going to suggest, let's just say that we've got 3 different key factors here that we know are going to be active, and that we would screen down, let's say, 8 factors in 16 runs. Okay, could be a good choice. This would be a nice number of factors to test. It's got a decent number of runs where we've got the power of 8 at the low and 8 at the high. So I kind of like this as an idea. Now, in this screening phase, which you'll see characterized by the yellow design colors on our design builder, our idea is that there might be a few that are vital that we haven't really explored before, but most of the factors in this screening of unknown factors will be trivial, as we would expect. And maybe by the Pareto principle 20-80 rule, maybe we would see about 20% of the 8 factors. I'm just going to be generous and say that 2 of the factors in this scenario come out vital, and the other 6 factors are going to be thrown off. But that's a win, because now we've got an additional 2 factors coming in. We're going to merge these together, and now we have a total of 5 factors at this stage, which is called characterization. Now, what we're going to characterize at this point are the 2-factor interactions. We're not going to worry about interactions that are greater than that. And so at this point, what I would suggest is you upgrade the resolution to a design that'll be shown in green color. This will be a high resolution design, or do the full factorial. So going back to our design builder now, let's say that we've gone to this next phase. This would be my favorite design choice, which has got 5 factors and 16 runs. And as it says up above here, these are characterization designs. And at this point, I'm also going to add in center points. All right, and I'll give you some examples of these in a minute, but adding center points is going to be critical at this stage, because potentially we could see some nonlinear behavior or curvature in the system, and putting in center points would be effective at this point. So I would say if we did the design with 5 factors and 16 runs, and I would suggest 4 center points, so this is a 20-point experiment. All right, so we do that, and there's a couple of things that could happen. One is that we would see either no significant curvature, or if there is significant, it's not important. And so then we would skip down to the end, and we would do a ruggedness test. Now, these ruggedness tests are also going to be 2-level design, but we're going to go into the red zone on these and do a low resolution, because at this point, we're hopefully able to get out to the field and go immediately, but who knows what might happen. And these were developer test methods that were put together in a very highly controlled, research environment. You go down to the plant environment, and we found a lot of issues, for example, on moisture determinations, where they had impure reagents. They had less trained operators for the method, and a lot of issues, temperature, humidity, maybe not controlled. So these ruggedness tests were developed by the American Society for Testing Materials, and I was a member of the committee that worked to revise the standard on ruggedness for test methods, which is E1169. And we introduced some tools like using half normal plots and things like that. But these ruggedness approaches can be used for processes very nicely, and I highly recommend them. Now, at this point, we want to get as many factors as we can. So we could go with, say, 7 and 8, or 15 and 16, which are saturated resolution 3 designs. Okay, that I wouldn't use these for screening or characterization, of course, but if we're just trying to do a go, no-go type study, these would be some choices. But at this point, I would suggest you drop down to a different option, which is called Plackett-Berman designs. And again, I'll talk about this a little bit more later. But what's nice about the Plackett-Bermans is that they allow multiples of 4. And so you could put 11 factors in 12 runs, which actually is one that I kind of like for the ruggedness testing. So let's just say at the end, and if we don't have 11 factors, that's fine. You can put in what are called dummy factors. But if you can think of 11 factors, then you can do this in 12 runs. And hopefully nothing would be significant or important. and you would be good to go and celebrate, and you'd be done. Now, what if there is curvature? Well, then we're going to go to a different design structure that's going to have at least 3 levels. And I would recommend the central composite design, for example, or a box Benken design. And these are designs that are available in Design Expert or SATIS 360. Here's the central composite. At this point, of course, you're not going to be running 12 factors. That'd be way too many. I would say maybe 2 or 3 factors might be good. And a box Benken is a nice option for just doing 3 levels of each factor. It's not quite as flexible as a central composite. Now, if you get the software, you can get it on trial, and you can learn about these 2-level designs by running these tutorials as a do-it-yourself, run all the way through that. And then if you're interested in response surface, there's a tutorial on that. And in that tutorial, it shows a picture of the central composite, which is the core of the 2-level factorial with the center points, and then with these axial points represented by stars sticking out of the sides to give you more levels and more leverage. Okay, so that's the basic strategy of experimentation. And oftentimes we refer to this as SCO, which is what DuPont called it when they started promoting this back in the 1950s. They called it the SCO strategy. And then I added the R to make a nice acronym of SCOR with the ruggedness testing. And this final phase, which is really confirmation, you could run, more advanced response surface methods even at this point to generate the quality by design space. But the quickest way of doing it would be the ruggedness test. Okay, so now I'm going to go back to my control panel, and I'm just going to ask if you're with me so far. Raise that hand button. All right, Wolfgang, thank you for weighing in. Gabrielle, and so forth. Okay, great. So I'm going to put the hands back down. Now this is where the recording will be handy because I've scribbled a lot of stuff on the slide here and nobody's going to be able to keep up with that. But you can go back and if you want to, recap what I just presented, look at the recording. Okay, so now let's move ahead and let's do a case study that demonstrates the SCOR approach from start to finish. And this is a welding case. It's basically made up. So you have to be aware of that. If you are expert in welding, some of it may not make as much sense as it seems like it should. Now, if you want to get a write-up on this, I did a presentation of this for the ITEA Journal of Test and Evaluation, which, T&E is a key part of developing national defense systems by the U.S. Air Force, which is our biggest client. We've also worked with the Navy. I've been out to the Naval Warfare Center out on the West Coast and U.S. Army. But U.S. Air Force is our biggest. And we're also going to be working now with the Space Force starting next month. So that's very exciting. So let's just say in this scenario, we've got a welder. This is a Navy welder. And we need to produce welds that will exceed the 50,000 PSI tensile strength. We're falling a bit short. So let's say we've got this engineering team and they do a brainstorm and identify 11 factors. 9 of them have never really been looked at before, so these are going to be subject to screening. So they considered 3 designs. One would be to study only the first 7 of the 9 unknown factors and then sort of give up on 2 of them. And this would allow the use of a standard 8-run design. Now keep in mind that 8 runs is going to be not real powerful with only 4 at the low and 4 at the high. Also, we know from looking at our design builder in Design Expert or SATIS 360 that if we go to the 7 and 8, that's a red design, that's going to be very low resolution. And so we'll end up confusing main effects with multiple 2-factor interactions, which is not a very good idea. So let's say that we reject that immediately because of the poor resolution. It's also got low power and we're missing 2 factors. So then we consider looking at all 9 factors in a classic 32 run design, classic or standard. So now let's say we go to the 9 factors, we're going to have to go to 32, but now that's too many runs and we're kind of overpowering things. So nope, let's reject that one. So then we decide that we're going to choose a modern minimum run screening design. These are optimal designs, but they've been formatted and templated, so you're always going to get the same pattern. And then if we add in 2 extra runs, that'll be good. And so I'll show you where that is. That is under minimum run screen. And the absolute minimum for 9 factors would actually be 9 times 2, which would be 18. But we warn that if you do that and you have 1 missing run, it's going to degrade back to the low resolution or red design. So we rebuilt this, and I give credit to Pat Whitcomb, the founding principal of Staties, and my colleague going back to the 70s, and Professor Gary Ohlert at University of Minnesota as our advisor developed these, and they crunched through all of it twice after doing all the crunching, which took about a year back in the day with the slow computers, and getting the minimum run part of it. Pat woke up one morning after a sleepless night and said, hey, we've got to redo this all with 2 more, and this is what we recommend. Now, we only have 20 runs here instead of 32. So if you're with me on this, that maybe this might be the way to go with the 20 runs, press that raise hand button. And I just want to see if you're buying into this idea of kind of, like Goldilocks getting just the right size. Okay, I'm getting some positivity coming back, so I appreciate that. And then I have a slide that just shows, where we're at with 9 factors, cutting down to the absolute minimum, but then plus the 2 would equal to 20. And that's what I would recommend. And you can see that this is going to be very advantageous to use these minimum run options for screening. And then we also have them for characterization as well. And so you can see that with these characterization designs, we can achieve a minimum run with a resolution 5, which will detect 2-factor interactions, but we can reduce the number of runs substantially. So here you see Pat and Gary having published his paper, which is available on our website. And then I gave a presentation to the American Society of Quality back in the day, talking about these designs. Okay, so now let's look at the welding case in detail, and let's look at these 9 factors. Now remember, there are some other factors that are being set aside at the moment, according to our strategy. And you can see that they've got a whole series of different things that can be changed from low to high to see if they have an impact. One of the factors is categoric. And then another funny little thing here is that the letter I is missing. We skip right from H to J because I is being used for the intercept, or in the technical jargon of design of experiments, it's the identity column. But either way, we're skipping past I to avoid reusing the same letter for 2 different things. Okay, now what I've got here is just some of the 20 runs shown here, and I've skipped by a bunch of them. But if you look at the tensile strength results here, you're going to see that we have some that are exceeding the goal of 50,000, and so that's going to be a promising outcome. Now I'm going to go ahead and go to the tool, which is Staties 360, but it includes all of Design Expert. And I'm going to open up this screening design. And then I'm going to do Control mouse wheel to reduce the size of this. It's going to be pretty small. But what we're going to see if we sort this is that there are some runs that are above 50,000. Let me Control mouse wheel this up again and then just scroll over to the right. And so we can see sorted out that there are some runs above 50,000. So that's good. Okay. Now, just to show you how this is built, is that we're going to be going with minimum run screen, and just typing in the names, the units of measure, the type, and remember this last one is categoric, not numeric. So we have alphanumeric information typed in here, and then you can see that we're using the +2 option. And it turns out with the aliasing of this that the main effects are aliased only with 3-factor interactions, and the 2-factor interactions are aliased only with 3-factor interactions. So it ends up being a design that, oh, I'm sorry, this is a screening design so that, well, like I said, the main effects are aliased with only 3-factor, which means that they're fairly clear because we could ignore the 3-factor interactions. But the 2-factor interactions are still aliased with other 2-factor interactions. So this is really only going to be good for looking at main effects. If any interactions come out, they're going to be, kind of messed up. But that's fine because we're thinking going into this that these unknown factors, possibly none of them will be, active. And if any are active, it'll only be 1 or 2 of them. And so we should be in pretty good shape. Now, one of the main things that we promote at Staties is that whenever you do a design, consider what difference that you're trying to detect. And let's say that at a minimum, they want to be able to see 1500 PSI, and then measure the standard deviation of your system and then do a power calculation to make sure that you have enough runs. And in this case, the 20 runs is going to be sufficient to give us at least an 80% probability of seeing the main effects. So that's an important, thing to do whenever you are doing a designed experiment, is make sure you don't undersize the experiment. And as I said in the ITEA journal, you always want to right size the design. You don't want to overpower the design either, because then you're wasting runs. So then we'll go ahead and open up the file with the data, which is over here to the right. And then very quickly, I'm going to do the analysis of it. I'm not going to go into a lot of the detail of that. You'd have to watch a different webinar to learn more about the basics of graphical selection of effects. You'll find a webinar that I presented on that. This design is not orthogonal. It's an optimal structure. It's not one of the standard classic designs that are orthogonal. So you have to give up on that a little bit. But basically what you're going to do is you're going to look for anything standing off to the right here. And it turns out substrate thickness, which we didn't realize, an angle, edge prep, and then there's an interaction, which we won't put a lot of faith in that, but could very well be that it is the angle and substrate that interacts. But this interaction could be any number of other things. As we see in this numeric table, you can see all the other 2-factor interactions that are going to be partially aliased. So we feel a little bit careful about putting much faith in whether it's really A, B, but it very possibly could be, because we've got the parents of A and B in the model. All right, and then a Pareto chart is always compelling to show with an ordered bar set, that these are standing out from the trivial many that are down below this black line. And the effects that I've picked are even above the more conservative Bonferroni limit at P of 0.05. And we see these good P values in our analysis of variance right here. And I can do control mouse wheel and make that a little bit smaller so that we can see both windows at the same time. Because I also like to look at these adjusted predicted R-squared, adequate precision, they're all good. I always check diagnostics. The main diagnostics that I like are the normal plot of residuals that are kind of falling in line, a la the pencil test, as we call it, or fat pencil test. I like to look at the residual versus run to make sure there's nothing outside of the red lines, no trends or anything like that. And then the Box-Cox plot is also a very important plot, just to see if it recommends the transformation, which it doesn't. So then in the end, we could think about, what's going on here. We're not going to pay much attention to this A-B interaction, but it could be real. But let's just say that it seems like we have found that there's a couple more things that we should consider, which normally I wouldn't show this graph with the angle being part of an interaction potentially, but let's just say that the angle is coming out of the screen as a vital effect. the effective substrate. We have to consider that and do some more work on that when we do the characterization. And then the edge prep, which seems kind of a no-brainer. Then they're pretty sure the welders were that they really do need to spend the time to do the edge prep. But they thought, why don't we try this without it and see what happens? And that did not really work. So it was a good learning experience, and they were able to find that there was 2 more factors. So there were 3 of them that did come out of the screening, which were the angle, the substrate thickness, and the edge prep. And we had previously held off 2. So now we have 2 plus 3, we have 5 that are going to come into the next step. So the edge prep, that was one that they decided they would just go ahead and say yes on that. All right, and just make that decision rather than trying to carry that forward, because it just was such an obvious thing. And what you can do is you can click on the higher level of this, which is the yes for the edge prep, and you can see that the LSD, least significant difference bar, doesn't meet it. There's a gap. So that's telling us that is indeed a significant effect, and we also can get that from the p-value. All right, now remember that I just don't have a lot of time to take questions during the presentation, so I know there's a lot of information coming in here. So be sure that you send me an email if you have a question, and just make a note of the slide. And this would also apply to any of you that are watching this recording, because it'll be posted and probably up on the YouTube channel for some period of time, maybe some years. And hopefully I'll still be around, and you can contact me, mark@staties.com. But we also have another email that I'll just throw out here that'll be more lasting, I'm sure. And this is in particular for our users, which is stathelp@staties.com. So this is available to anybody that's using our software, or they're using a trial download of our software. Okay, so moving ahead then with our welding, we're going to move to phase 2. And since we've set the edge prep, then all we're left with are the 2 known factors that bypass the screening, which are the current, which is a change in the amps, and whether we use stainless steel 35 or stainless steel 41 was another one that was a known factor. Now we have 2 more factors being thrown in for this next phase, which is characterization. And remember, this is going to be either a high resolution green design or a full 2-level factorial. All right, so considering if we have 4, then the full factorial would be 2 to the 4th, which would be 16 runs. If we try to do a fractional design on 4 factors, let's just set up a new design here and just look at what would happen. So if we have 4 factors and we try to do a half fraction, that's going to become a yellow, which is the screening design, and that'll still have the problems of aliasing of 2-factor interactions. At this stage, we can't handle that. We need to have something that will resolve the 2-factor interactions. That's why we're doing the characterization. In this case, they added 3 center points. I like doing 4 center points. I think it's just a little bit better. I would recommend 4, but 3 is okay. So they did 3, so that's what we have to deal with. And so let's see what happens next. Okay, so as expected, all 4 factors emerge as main effects or were involved in the 2-factor interactions. And so we're going to move on to the response surface methods. And it says that there's no time to demo this, but maybe there is time. Since I've presented this a few times, maybe I should demo that. So I'm going to demo it. Let me just ask the group, though, if you're okay with me showing this design, just so you can see what happens with the 2-level design with center points. If you're interested in seeing that, press that raise hand button. Okay, yeah, I'm getting some affirmatives on that. So let's just see what happens. I have it actually teed up here already. And you've seen how you set up a two-level design with center points. This happens to have 3 center points. You can see the 3 center points here. Now, what happened was we thought we were going to do just 3 center points, but because we have a categoric factor, there's going to be 3 at each level of the categoric. So actually 3 is not a bad idea, because you're going to get 2 degrees of freedom from the 3 that are done with the first stainless steel, and 2 degrees of freedom from the second one, for a total of 4 degrees of freedom for the curvature test. So actually that, because of this categoric factors, the 3 is not a bad idea. And you would see this, if I would have picked 4, it would have been multiplied out, because we see this warning here. So that's good that I showed that. And we say yes to continue. And then we do a power calculation on it. And I don't think these numbers are quite right, because it seemed to me we were looking at 1500 before, and I thought it was 900. So I'm not, I think these power calculation numbers might be a little off, but you can see even if I reduce the signal and if I also have less noise, then, you know, it's still good for detecting main effects and maybe some two-factor interactions. So now I'll go ahead and open the data. And of course, I won't be able to spend a lot of time on this, but we're going to use this half normal plot. And by the way, this design, they chose a full factorial with center points, but because of the way it's structured, it's not orthogonal, but it's nearly orthogonal. And I'm just going to drag over these ones off to the right rather than picking them up one at a time. And you can see that there's definitely some standing off to the right here, including some interactions. And so we see that we've got a fairly complex situation here. And one thing we want to make sure, though, is that there's no significant curvature. But there is significant curvature. Whoops. Okay, so that's kind of invalidating things at this point, really, to use a two-factor interaction model. And so we're going to want to augment this to a response surface method and not spend much time working on it. But I can show you what's going on here is that if you look at the 3D surface, you'll see that the points in the middle are sticking way up over the surface. Okay, something is not right about this. We can twist this plane, but we can't get it to go up at this point without having multiple levels of each factor. And so this calls for a design augmentation, which can be done readily using the STATE software. And oftentimes it'll recommend doing a central composite because of the structure of this one and saying an RSM optimal design. But we're going to take a little bit of a different direction here, because to keep things simple, the engineers decide that they're going to eliminate this SS35 stainless steel and upgrade to the stainless steel 41. And if we were to pull up this interaction of A and D, we would see this particular picture showing here. Here it is here. Okay, you can see that this green line, which is a stainless steel 41, is definitely over the top. And at the center, these green points, which are the SS41, are higher than the red points, which are the lower grade stainless steel. So that's a decision being made, you know, by the subject matter experts, and only carrying SS41 forward at this point. Okay, so one of the nice things about knowing the SCOR, the strategy of experimentation, of screening characterization, optimization, and then ruggedness testing, is that you have options along the way. You're not doing one giant experiment. And one of the general rules of thumb is to put no more than 25% of your overall experimental budget into any one experiment or group of runs. And that leaves you flexibility to do 3 or 4 different experiments, you know, which are actually a collection of runs that are done via DOE principles. And this is illustrative of that. idea, it's a big payoff, because each time you finish one of your experiments, you can make some changes. You don't have to keep going with the same factors. You can change the levels. You can maybe throw in some new factors. And so it's very flexible. So at this point, we're going to go to the response surface method because we are seeing curvature, and it's important. Okay, if it was just a slight amount of curvature, if it was significant, it wouldn't bother me. But what's really the focus is it important? Is it something that we need to know about? And the answer is yes. So at this point, then we're applying the response surface methods, but rather than running across the entire mountain range that we could operate within, we're going to focus on one peak here. And by achieving this focus, we can fit with just a simple polynomial model, and it just needs to be a quadratic that has, the squared terms embedded in it. So the model that we're going to use will predict the response y as a function of the main effects, let's say for two factors, the interaction, which we can get from a factorial. We can get this from a two-level factorial, but we're also going to approximate the squared terms, and this is going to require a response surface method that has at least 3 levels. And this technique was developed by George Box, as I think most of you know, and you probably have heard his saying, somewhat paraphrased, all models are wrong, but some are useful. So it's an empirical approach. So now we're at this phase of optimization. We have seen that there is significant curvature, and it is important. We actually had 4 factors, but we're fixing the steel at the higher grade of SS41, so that leaves us with 3, which is going to be a much more doable experiment. So now we do this central composite I showed you in the tutorial from the software. The shape of this is a cube with the center point, and the center point actually will be done a number of times. I usually draw circles around it to indicate that, because we do want to achieve a focus at the bullseye here. And then we're going to push out from the original range with these axial points. And a lot of people will take these axial points and move them into the face and create a face-centered central composite. However, that loses, some of the properties we like for rotatability, in particular, having equally precise predictions equally distant from the center. So that if you're going to move those star points in, there's actually another option that's called the practical alpha that I would recommend. But if you can run the original structure of the central composite with those star points outside of the original cube, that would be better. Okay, so just to make sure that you're with me at this point and that you buy into the sequential strategy, give me some positivity with that raise hand button. And there's a method to my madness here, because thanks, Peter and Yun and so forth. I'm just sitting here at my winter home in Florida and presenting to a screen. So I need to get that feedback to make sure that my communications are working. Okay, thanks again for being active in participation. So now we're going to do this additional block of runs, which are going to be added in using the tools of Design Expert. And we're going to create some additional center points. And this is being laid out in, right now, I think this is in standard order. So the order of this is going to be randomized. But what we see is that we're getting a lot of green numbers here that are above our 50,000 goal that we had. So we're really starting to make progress here at this point in knowing what the critical vital few factors are and where to set them. So I'll go ahead then and open that file up, which is the optimized file. And here it is here. And you can see the space types are listed. And then the actual order of this was randomized in the second block. You can see that which is really important. But when we sort this, we're going to see that, we get in the second block, some really good results that are over 50,000. You can see them here. Okay, so let's take a look at the analysis of this. And it turns out that it's advantageous to fit the quadratic to this data, which is what we designed the experiment to fit. That's what the central composite does. Or you could do an optimal design to fit a quadratic, and that would work. And we see that the quadratic terms themselves are very significant. By adding those quadratic terms, we eliminate significant lack of fit that we were getting with the two-factor interaction model. We saw that before. And we get really outstanding adjusted and predicted R-squared values. So the quadratic is definitely the way to go. What we could consider would be a model reduction. It wouldn't be very effective though, because we need to keep the angle substrate angle in the model to support the A-squared term and create model hierarchy. So we wouldn't want to get rid of angle. Possibly we could get rid of this BC. We do have an auto select option, and if we set alpha out at 0.1, that does take the BC out. But to me, at this point, I feel like we're kind of splitting hairs. So I would leave the BC in if it was me, and just go with the full quadratic model. But this is where George Box said all models are wrong, some are useful. So if you decided to get rid of BC, that you wouldn't be wrong to do that. I don't think it would have much of an impact either way. And we look at the diagnostics. One of the things you could do is try different models and see if it changes the final outcome. And I'm certain that it wouldn't in this case. So now we get a really good picture of what's going on with these factors. All of them are having impact, and they're all having curvilinear impact. I can see that from this perturbation plot. I don't know if you can really choose between these three factors in terms of how they're affecting things. So now we're going to go to the 3D surface, and then we can slice this current. We can move this up or down and see what it does to the surface. But we want to increase that tensile strength. So I think going off to the right is going to be the way to go here. And then, we could use the software to find a maximum outcome. And we said we wanted to get to at least 50,000. So I think I would type that in as a lower threshold. And then I would just put a stretch target at the top here and see how far we can go. And I like looking at the ramps rather than, I like looking at graphs a lot more than numbers, but even better yet are graphs with numbers. And so here we have, a visual of where the factors are located by the red dots. And we can see where the response is coming out by the blue dot. And so this would hopefully be a winning combination. And the only other thing I would do, which we're going to talk about next, is I would do a confirmation run, and a ruggedness test would be the best. But at the very least, I would do a series of confirmation runs, and I recommend doing 6. I wouldn't do just 1 for obvious reasons. 3 is a popular number, but I think that's a little bit weak. I wouldn't do 100 confirmation runs, but I think 6 is just about right. And then we could set these parameters, let's say for the angle and for the substrate thickness, to some convenient level. And then we would collect the data here. Whoop, I did the control mouse wheel and I got a little bit carried away. So what we're going to do then is put the numbers in here for the tensile that we get, and hopefully the numbers would be good, and they're going to flow down into this field here for the data mean. And as long as we're between the prediction interval, which will adjust as we add more data here, we're good. But if something just went completely haywire and we got only 30,000, something has gone bad, probably a special cause, and now we're not within the range, and so we would have to say this doesn't confirm. But in this case, it did confirm. Okay, so that is an extra little thing that I don't have a slide on, but I highly recommend it. So we must confirm this, and I would start by first simply run 6 at the set point, the new set point. Okay, and if that's within the prediction interval, then you're good. But a more active confirmation would be to do a ruggedness test. And the reason I'm saying that is because we could make this work at the lab, you know, for the welding, okay? But what's going to happen when we go out to the field? Let's say the U.S. Navy is going to start welding, you know, with these new conditions. Is it going to work there? Because now we're, you know, out on the West Coast at some manufacturing operation. It's, you know, got very high temperature, low humidity, or maybe we're out on the East Coast and the humidity is high, things like that. And what about the actual welders? Well, they should be very well trained, but they may not be as trained as well as we are at the research center. And so that could have an impact and things like that. So we have to consider what are the factors that might be applied once it gets out to the field. And in the military, this is, of course, you know, pretty vital. And I mean, something happened to this laptop here. I'm not sure what, they dropped it, you know, down into a well or something. Is it going to hold up or is it going to break up? So it's a special application of a statistically designed experiment. It allows for many factors to be put into a minimal number of runs, and we just do 2 levels of each factor, and this is spelled out in this ASTM standard, which is related to test methods, but it works equally well for process or product. And so what I recommend for this is we shift over from the standard 2 level to this Plackett-Berman design, and doing a little bit of studying brought up some interesting stories about Plackett and Berman being guarded by the military in UK at a Scottish castle because they had these test plans that they could produce for development of ordnance. And so they were, you know, it was highly classified and they were very important people. Now, with the Plackett-Berman designs, you're able to work with multiple of 4 versus the powers of 2, and that's a big advantage. And then we can saturate those. If we don't want to fill it out, we can put in dummy factors, and we can just kind of ignore what happens with the dummy factors. So this will be a resolution 3 design, but you can fold it over and form a design that's resolution 4 by putting in a second block of runs. So it's kind of nice to run, because if nothing turns out to be significant and it's not important, you're done. If it turns out that you have important effects, then you can fold it over and you can build up the resolution to 4. So in the engineering case here with the welding, they identified 11 factors that would be of concern, things like ambient conditions and the like. And they set, you know, ranges that were fairly wide, that should span the majority, maybe 95% of the normal variation based on historical records. Okay, now we have some different things that could happen here. And one thing would be that we could get nothing significant that would be a flat line on this normal plot, but the magnitude, absolute magnitude of the effect could be quite large. And so let's say that in this case, well, we're talking about tens of thousands of tensile strength. 217 is not very big. So in the left-hand case, we've got something that is insignificant and unimportant. So I would say that's pretty good. Do you agree with that? Press that raise hand button if that was an outcome. Okay, I'm getting agreement on that. Okay, now another scenario is that we could see things turning out significant because they're off the line here, and it could be quite large. So this one is significant and it's important. So obviously this would not be Very good. So what did the engineers see in this case? They saw this. So that was good. They didn't have to go back and do further work and resolve it. So that completes my presentation for today. We're up to the full hour almost with just a couple minutes left. So what I say is it's good to know the SCOR, that you understand there's a strategy of experimentation that's tried and true going back to the 1950s and continuing on from there with DuPont's SCO strategy. And so all I've done is added on at the end the R, because I do think this ruggedness testing is really the most conservative approach rather than just simply repeating the same set point over and over, under the ideal conditions at the R&D center, to actually go out to the field, understand what they're going to be facing out there, and then see if your test method, your process, or your product is going to continue to operate the way you expect. And I've seen the answer being no quite often. For example, with test method development, we had some pretty major failures of test methods transferring from Minneapolis to our plant in Kankakee, south of Chicago. For the reasons I mentioned earlier, they were recycling reagent, they were using, a different level of operator, they didn't follow the method procedures, they recycled reagents, they did all kinds of things. And so that should be done before we finalize the technical transfer. We should be running that ruggedness test. And you could even run a more advanced, response surface method to make sure, that it's going to confirm. And if it to go back up and kind of start over your program, but if it's a ruggedness test with the Plackett Berman, you can fold it over and you create a design that has twice as many runs, let's say 24 runs. So if it's a PB12, you'd fold over and you'd have a total of 24 runs, and that would be a second block. And it's real easy to do using the software. So for example, if I pull this ruggedness test up for the welding, and it turned out that 217, you can see it here at the bottom, and it's got a straight line. So that was good. Okay, but let's say it wasn't good. Well, then you would simply go to Design Tools, Augment Design, and already it's set up with a fold over. You just say okay, and we're going to fold over on all the columns, and we could do a design evaluation, but you can see now we've got a second block of runs, and in the second block of runs, it's opposite. So where it was plus, it goes minus, where it was minus, it goes plus, and you can see these columns have gone completely opposite. And so it's 8 or 12 new runs in this case. So the resolution of this now ends up being resolution 4. And so we're able to detect the main effects alias only with 3-factor interactions. And so no aliases are found for the main effects model. And of course, our original design for the ruggedness was resolution 3, so that all the main effects were aliased with 2-factor interactions. And so in that case, we didn't have the resolution we needed. I've got to put in the 3-factor order. The main effects were fine, but the 2-factor interactions weren't. So to wrap this up, I suggest as a reference that you take a look at the simplified series that I'm the main co-author of, with all the mathematical backup from Pat as my co-author for the first 2 books, which cover the process side of things. And then Martin has worked in, our current CTO and president, and PHE statistician into this formulation simplified. And that would be the thing to look at if you're interested in doing mixture design for optimal formulation. But what I've covered in this presentation is covered in these first books, DOE and RSM Simplified. Oh, by the way, as another precursor, other than making a fantastic invention like Art Fry and so forth, was recommended by Paul Nelson at our UK value-added reseller Prism TC, and he recommends you doing what's called a scoping design, where you just do what are called forcing settings, which is forcing it to a very severe level in this red condition, and mild settings are at this lower blue condition, and then repeating the center, and just trying to get an idea of whether you're even in the right range by exploring extreme settings. And Doug Montgomery, suggests that it's really important to spend a fair amount of time before you start the first design experiment to plan, what's going to happen, to make sure that you've got, a decent set of factors and the ranges are reasonable. So I really advise doing range finding at the start. So in conclusion, benefits that we see are tried and true path to process improvement that's flexible because of it being iterative. And it really cannot fail to be productive if powered properly by sufficient runs, whether it meets the objectives or not because of process of elimination. And by breaking the R&D into small steps, it allows you to react along the way and thus reduces wasteful runs. If we would have started with 11 factors from the beginning and done a complete RSM design, that would have required 96 runs, whereas we only use 50, 20 for the screening, 22 for the characterizing, and 8 for the optimization by adapting as we went along the way. So it was about half the number of runs, and it got us a much better outcome with a lot more information. So the WIFM by example to lay out a strategy, hopefully you could see the advantage yourself on that, and mapping out a sure path, hopefully that you can see the advantage of what's in it for you on that, and that this is something that was helpful to you. So I'll just finish up by just asking, do you agree that this was a useful presentation? Yes, I hope so. Not that I want to bias the results, but go ahead and throw those hands up. And thank you, Wolfgang, clear and comprehensible presentation. I appreciate that comment. And that's all I've got time for. So we'll just wrap it up and say, all the best to you. Consider, sharpening up your skills with the training. That goes without saying. Feel free to contact our workshops team if you have an interest in that. We have various public courses, available. So again, thank you, and all the best to you. And I'm happy that you know the score. Take care now. Bye-bye. Oh, by the way, email questions. See you.